thought you got rid of it.
IRAF.
All right, who's reduced data with IRAF then? Oh, not too many people. Anybody use the Gemini IRAF package?
Oh, yes.
Oh, yeah.
I wrote a whole webpage about it.
Well, this is for you.
About using it? Yeah, about using it to reduce multi-spec data.
Well, it can be painful. This is for you. So I work with IFU data a lot, from the GMOS IFU mostly, which is optical spectroscopy. And I find it takes me a long time to reduce data. It can take, a year or two to reduce a handful of observations. That's tended to include a lot of process improvements and things. It's not just scripting reduction, but this time we have a larger data set for the project I'm working on now, and I decided it was about time to do something about the state of the data reduction, because I've made some improvements to the quality of the RF processing recently, and it's not perfect, but it's acceptable. But it's just a lot of work to script a lot of things like repeated file names throughout the data reduction scripts, process not being separated from the data generally. So the commands that you have in your script tend to be very specific to the data set. Not all of the processing steps have the same kind of support for passing lists of files and things. When you want to reprocess your data, you have to tend to delete some of the files that you want to reproduce, and then comment bits of the script out, and then rerun it. And if you make a mistake, it can take several hours before it crashes, and you have to do it all over again. And then you end up with a script that you're not quite sure what you actually did. You have to select all the calibrations manually. You have to sort of say this bias goes with that flat, and that flat goes with this science observation. Spell them all out without any typos on the command line for each processing step. If you want to tell, switch whether the reduction's interactive or not while you're still getting it right, you have to do that separately for every step. Same for whether you want to propagate errors. There tends to be a lot of boilerplate code sort of overriding parameters so that they're more suitable for the IFU rather than long slit spectroscopy, things like that. The whole thing tends to be quite verbose, so I end up with a 1,000-line CL script that you can't quite see what the description of the process is at the top level. Some of the processing steps are quite monolithic, and there are some obscure workarounds and things in there. I don't really have time to show you an example, but there's one at this URL if you're really feeling masochistic. So I mean, it's just a lot of work to process new data sets, and I decided to do something about it. I'd also like to be able to insert new Python steps, of course, into the process and to operate with Astropy, which is something you can't really do in CL. So instead of spending the time on a lot of monkey work, I've rewritten the process as a Python script. There wasn't really a suitable existing tool I could use to use our existing IRAF code with potential for Python compatibility and also a reasonable development effort and risk. I could have tried to use the Gemini pipeline, for example, but it's such a big thing compared with my effort that there's a high risk of running into tip of the iceberg type problems. So the emphasis here is very much on convenience and productivity. It's not extreme performance. You probably would reduce your LSST data with it, but it's not gratuitously inefficient either. I'll kind of cut to the punchline a bit here since I don't have a lot of time, but I've drafted this Python module called ndmapper, and it's basically a sort of toolkit to allow you to script the IRF process in Python simply in an automated way. I think there's a pointer here. So the kind of core thing that you see is this library of processing steps, which mostly contains GMOS IFU spectroscopy steps at the moment, but it's designed. It could potentially have steps for other instruments added to it fairly easily. Most of those are actually wrappers, fairly simple wrappers for IRAF steps at the moment. There are a couple of pure Python steps in it too. I also have this IRAF task runner, which makes it easy to wrap the IRAF tasks. A representation of the data that we want to propagate between the steps, a few utilities, and then these calibrations and services modules help to automate and find the calibrations that match the science observations and put it all together in an automated way. And then there's this IO layer, which is ultimately calling IO.fits at the moment for the data access objects to use. But it's abstracted and could use other backends like Astropy. Oh, this didn't quite come out how I thought, but I'm considering splitting this into two modules, one which is closer to Astropy, and one which is dependent on IRAF and PyAstro, which I'm interested in any feedback on if people are interested in using this. I'll just talk mostly about the data representation because that's the bit that's probably most relevant to Astropy and ND data that people might want to use in pure Python processing code as well. That's pipeline-like. So I have this. So if we look at a fits file here, we can open it up in io.fits with this convenience function and see what it looks like. It contains a binary table with some information about the IFU setup, and the image extensions are called SciVar DQ1 and SciVar DQ2. They're basically a main science array, an error array, and a data quality array for part processed data in this case. And they kind of conceptually map to the data uncertainty and flags attribute in ND data, or potentially mask attribute. This is a discussion we were having yesterday, but I'm using flags at the moment. So I have this data file object. You can open up a file name in it like this, and you end up with a thing which is basically a list of ND data instances of length 2 with these extensions mapped to it. And you can change a convention in the package. If they're called something else in the fits file, you can change the convention in the package configuration. So this object has a meta attribute like ND data, which is, in this case, it's the fits primary header. If you look at the first element of the list, it's basically the first ND data instance. It has a data array, an uncertainty array, which is at the moment standard deviation uncertainty, but I'm meaning to subclass a variance uncertainty as well. It has flags there, which is data quality, which is all 0 here. And then the ND data meta extension is the image header, Sci image header. So the data file also has a file name parser object in it, which keeps the file name. And you can use that pretty easily to split up the file name into its components. Change processing prefixes or suffixes or whatever, and see what the extension type is. It's pretty easy to cast one of these to another and make modifications like adding a prefix or a suffix to it. And you can check whether these things are equivalent, have equivalent paths and things like that. If you can cast the whole data file object to a string, and it basically reduces to a file name like this, which you can pass to IRAF, which I'll elaborate on why in the next slide. If you want to make a new instance, you can just create a data file with a name and a different mode that's writable. Say append a couple of ND data to it, and then you end up with this length 2 data file. Each ND data instance has an identifier, which in this case maps to the fits xver, and so you can just do df.save, and you end up with a file on disk that looks like this. It has 2 sci extensions in this case. They're in 64 just because that's what NumPy did by default, because we didn't tell it otherwise. So like I said, the fits IO is abstracted into a replaceable backend, but it does have a couple of fits-like assumptions. It requires a flat list. The file has to, the list of ND data instances has to be basically a flat list in the file, and the identifier has to be an integer at the moment. But I'm hoping to support maybe asdiff at some point for propagating GWCS and that kind of thing. Binary tables get propagated in Astropy table instances. That's working at the moment, and you can, I just haven't defined the public API properly, but that's kind of a delta on what I've already done. But at the moment, any table information does get loaded and saved, so it's not lost. I haven't got around to propagating unrecognized image extensions yet. Pixel data are actually lazily loaded, so it uses a subclass of ND data array, which I couldn't resist calling ND later, to do lazy loading. So basically, when you instantiate a data file object, it passes the file and it keeps a proxy object in this ND data subclass, which tells it where on disk to get the, what file name and extension number and so on to get the data from. And as you access .data, for example, it will just load that on demand. It's not especially efficient, but it's not a big deal compared with some of the efficiencies we're dealing with in IRAF. Saving's a little bit more optimized. You didn't expect the Spanishing position. Moving on. So I also have this file list object, which basically keeps a collection of these data file things. the moment, it mostly serves just to be able to instantiate a load of these all at once. And you can, just give it some file names or existing data file instances, modify them with a prefix if you want, and there you go. You can append one to it too, and you end up with a list of data files. It's pretty easy to envisage being able to do operations on a whole list of these things as well, such as saving them all at once or adding 2 lists or whatever, but that's what it does so far. So that's what I'm propagating, and I think it makes a decent model in Python as well as IRAF, but I have this IRAF task runner that I can basically feed these data file objects or a list of data file objects to IRAF with IRAF tasks. So if I take a data file list here and then I make a flip copy of it, and I want to use this gem_arith task to add the 2 lists of files together, one by one, then I can just give them to this run task function. It takes the fully qualified name of the IRAF task, and then it has a dictionary which maps data file lists to IRAF parameters. In this case, I called operand 1 and operand 2, and an output parameter to, in this case, it's using this special syntax which basically says base the file name on the input file names. That's what the @sign means. On the operand 1 file names, adding the suffix test1, and then after these special arguments, you can just continue with all the usual PyRAF task arguments. And it can do this on simple, it can do this with, so Gemini IRAF tasks are aware of MEF files and know what to do with them, but if you have an IRAF task which isn't like IMARIF, then it can also loop over the FITS extensions for it and add them one by one as long as they match up. So if you run that, it just does this, runs the task, checks that the output file was created properly and raises an exception if it wasn't, does some stuff with the logging, takes care of iterating over the files for you. So basically, and then it returns this dictionary of data file instances mapped to this result parameter. So we basically effectively just ran an IRAF task on a Python object there. If the data files may have changed in memory, then they get saved automatically by this run task function for IRAF.
3 months.
Yeah. All right. So on this slide, I'm basically just saying that I'm redefining each of these things has a thin wrapper which allows me to redefine the API in a cleaner way, and it allows me to do stuff like obeying global settings for uncertainty, which is done automatically via obeying global settings for things like interactivity, which is done automatically by a decorator function, so you don't have to worry about it. And these things look pretty much the same as pure Python steps with doc strings and so on, and it allows me to define an API that I'm happy with, and I don't have all of these parameter overrides and things in the top level script. It's relatively easy to add a pure Python step to the processing library as well, just sort of loop over the ND data instances and so on. I was hoping to make a meta decorator for Python processing functions that does some of the stuff that runtask does for IRAF and handles some of the iteration automatically. Okay. Oh, and so a nice option is that the package can basically, you can tell it whether to reprocess files. I'll come on to that in a second. And then these calibration and services modules allow you to look up, in this case, for Gemini data, the calibration matches are determined by an external web service, but they allow you to look up calibration matches to your science data recursively, so you can get the flats for the science data and the biases, and then the biases for the flats and so on, till you've got everything you need. There's a couple of steps for downloading files and for matching calibrations, and they become no-ops once the information that they retrieve is complete, so you can rerun your processing and get reproducible results and work offline. And then there are a few support functions that allow using that information in one line. Most of this is not Gemini specific, so it could be of use to other people. The calibration matches, when that information has been retrieved, it gets saved into a JSON file that the user can edit to override matches if they want to, and anything that you put in there is respected and doesn't get overwritten if you do a new lookup. So the whole process ends up looking a bit like this. It's got some imports because it's a Python process. At the top here, you can set some package level configuration like log file name, whether you want to interact with the data by default, the processing steps. This reprocess, if you set it to true, it will automatically overwrite any files that already exist when it's processing the data. If you set it to none, it will complain if the files exist, and if you set it to false, it will reuse any files that already exist. So let me, it'll reuse any files that already exist and skip the processing for that step, which is pretty handy when you're developing the process and adding bits to it. For example, what would take about half an hour to run can take 20 seconds or something like that. So here, this is the only place in the script where there are any file names. Of course, it could be a command line argument instead of being hardwired here. Those are a list of 3 science files. This download files functions gets them to local directory if they're not there already from the Gemini server. They get cast to a data file list. There's a lookup function which will find all the calibrations for them, matches for them, put them in calibrations.json, and it reads them from there if that already exists. Then you can give that information to download files too, and so it will get all the raw files that you need to process your calibrations, and then you can basically iterate over the specific types of calibrations in the dictionary using this cal entries thing. So in this case, it gives us all the biases, and we can iterate over them and run make bias on them, and then keep them in a dictionary for later use. And so the same is true basically for. Was I out of time there? Am I going over? Yeah.
Oh, you're into questions. That's
okay. So
you get to make your decisions.
Okay, there are 2 steps in this thing. Currently, there are just 2 steps in this thing that aren't completely generated. This one because it has pixel numbers for making a bad pixel mask for the detectors in it, and there's one lower down where it needs to know where to find a standard star spectrum in 1D spec. But most of this is basically completely detached from the dataset being processed. So iterate over flats to get initial traces, do the arcs, iterate over the flats to make the final flats, and then make the standard star here. And then this is the science reduction at the bottom, and it's basically just a script that feeds one step into the next. It does a prepare, subtract bias, associate cal. Associate cals is just telling it which biases, for example, go with it, which science observation it associates that information with the data file for the next step to use. So it's doing bias subtraction, spectral extraction, wavelength calibration, sky subtraction, flux cal, resampling to a cube, and then at the end you can just do that if you want to and see what the data look like. Just as an example. So it's on PyPy if you want to see it. You can install it with pip install. There's some basic API documentation at Read the Docs. Source code's on GitHub. I just about got Travis working yesterday. So I'm curious whether other people are interested in this. I haven't given a talk on Good Friday before, so don't forget whose day it is. There you go. I'll leave you with this if you want to try it out or if you have any questions. Right.
Questions for James? I have a question since I've actually used Gemini IRAF a lot.
Okay.
What is the anticipated? So you said you have basic API documentation. When thinking of a typical grad student who just got all this Gemini data and is like, okay, what do I do? How do I get out my spectra? What's the route that they can take for using this package? For learning how to use it. I mean, where's the cookbook?
I hope to, so I plan to put up this example at some point. It's not quite science quality yet. It's missing a couple of sort of second order processing steps.
Okay, but now I see. So this can be pretty easily transformed into a cookbook. Yeah,
I mean, I would. This would serve as an example, and I should probably write some more narrative documentation as well. I just haven't done it yet. I'd like to. I will announce this on the Gemini Data Reduction Forum at some point when I've progressed a bit with the project.
Okay.
As well, but it should be. So this would serve as a starting example, and it should be relatively easy as well if people want to reduce data from other instrument modes to add steps to the library.
Oh wow!
I didn't show you that because
right.
It's not very long.
So it's expandable to other instruments.
Yeah, I mean, the wrappers are basically they're more or less run task call plus a couple of boilerplate calls, but they're quite short, so it's pretty easy to add steps to it, even for a non-expert.
Other questions? Because I have another one. How has the Gemini administration been supportive of this effort?
I uncover it. I think Gemini administration has been pretty supportive, actually. So we have an official pipeline project at Gemini, and it's more focused on data quality assessment. This is a lot simpler than that. And, you know, I've done it for the science project. I would say we've had some reorganization lately, and I'd say people are relatively supportive of scientists doing stuff on their initiative and making it available to users.
Okay.
So, yeah.
Good, that's good. All right, let's thank James again.